thank you for joining us today on this podcast. I'm your host, Robin Mitchell, and could you please give us a bit of information about yourself, who you are, and what your company does?
Thank you. Great to talk to you. So my name is Scott White. I'm the Chief Executive of Pragmatic Semiconductor. We make unique, flexible integrated circuits, so the equivalent of the silicon chip, but with no silicon, which means we can make it extremely thin, flexible, and very low cost. So our wafers, as distinct from silicon wafer, look like that, very bendable, thinner than a human hair, and typically about 10 times lower cost per circuit than could be done in silicon. And so the idea of this is not to replace silicon in high-end applications where you need the performance that Moore's law has been driving over the last several decades, but more about how you add intelligence into things that you might not previously have considered possible. So often things that aren't boxes of electronics, but being able to embed it into those sort of thin, flexible, everyday form factors.
Right. So the first question I actually have about these flexible devices is that you've created integrated circuits with a silicon equivalent that's flexible. But my first question is, the substrate, the actual semiconductor substrate itself, is it silicon still?
No, there's no silicon in it whatsoever. So the substrate itself is actually just a plastic. It's literally just a physical carrier to hold everything together.
Right.
And that actually forms most of what you see in the wafer is just the plastic that holds it all together. The actual electronics layers are a total of about 2 microns thick. And they're formed of a series of different layers for the semiconductor, the dielectric, the metal interconnects, and so forth. Each of those is a different material. But if you want sort of what's the direct analogy to the silicon, it's a metal oxide semiconductor layer that we use to actually form the transistors and diodes and other active semiconductor devices.
So the way that I understand metal oxide semiconductors is that typically you have a semiconductor crystalline substrate, and that might be something like silicon. I think maybe gallium or germanium, those types of metals. Depending.
Yeah, if you look in for integrated circuits, it's always silicon.
Yeah.
If you look at sort of other types of semiconductor devices, so things like power electronics or LEDs and things also use other semiconductor materials like gallium arsenide, indium phosphide for some of the photonics and things like that. So there's a range of different semiconductor materials with different properties, but as you say, they're typically all formed in a rigid crystalline wafer. And then the way you create the actual devices is by patterning and changing the characteristics of those crystals in order to create the properties you want.
Yeah.
The difference with the kind of approach we take is, as I said, we start with effectively a non-functional substrate, and onto that we deposit a very thin layer of the semiconductor material, and that means as deposited, we already have the right characteristics in that material. And so the huge benefit to that, as well as the form factor, when you look at the sort of cost of the materials in the process, is that we don't have to do any of the very expensive processes you tend to find in front-end of line silicon chip manufacturing, like ion implantation and diffusion, the things that are actually changing, creating the P and N type wells within the semiconductor material in order to create the transistors themselves. Those are the bits that are very expensive, very high temperature, long duration processes in a already very expensive single crystal bit of silicon. We don't have to do any of that.
So just to be clear, when you create silicon wafers and you do things like ion implantation, so you grow like a mask on top, you apply a mask on top, you etch the areas which you don't want, and then from there you can fire ions up to this thing to implant your to create N and P wells. But and you're saying that specific process as well is quite expensive.
Yeah. So if you think of it, the two things that make that very expensive in silicon, one is the granularity of the patterns you're trying to create in it. So the smaller the feature size you're trying to drive, the more expensive that process is to actually create that mask effectively on top of it. But then the other piece that is also very expensive is then that process of, once you've created the mask, what are you actually trying to use it for? And if you're trying to physically change the characteristics of the silicon substrate, which is what you have to do in non-electronics, that is a very expensive high temperature process. So again, the differences with us is, that latter piece we avoid entirely because the materials are deposited with the right characteristics from the start. We could, and then in terms of the the size of the features, because of the types of functionalities we're aiming for, we're not trying to drive down to, sub 7 nanometer features like silicon is
of course.
at the sort of, bleeding edge of Moore's law. And so a lot of those other things become a lot lower cost as well.
I think you'll find it's 3 nanometers now. it gets ridiculous. It's getting ridiculous if you ask me. It's ridiculous. 7 nanometers is old. 7 nanometers is old now. But by the time you hear about it in the news, Samsung, they're already doing. I think they're taping it out soon, 3 nanometer. But
I think one of the interesting things to pick up on that though is that although it's the continual progression to smaller feature sizes is what tends to always hit the headlines, because it's sort of the exciting bit that costs tens of billions of dollars and is obviously important in driving the high-end functionality we need for AI and increasingly more sophisticated microprocessors. When you look more broadly across what electronics is used for and the range of functions that are needed, there is an awful lot there. In fact, the majority still is done in older generation technologies.
Of course,
because they don't need more performance. And that, to a certain extent, is part of the motivation for what we're trying to do is when you look at those kinds of functionalities, you don't need that high performance. You don't need the incredibly small feature size. You just need it to be good enough to deliver the function that's needed. And so you take, as one simple example, the sorts of things that have been holding up car production in the UK over the last couple of years, in general terms, have not been high-end silicon. They have been things that do relatively simple functions. There was one that was widely reported, which was the $1 controller for the heated seats was what was holding things up. That doesn't need a 3 nanometer process.
Exactly.
It doesn't get any better if you try and put a 3 nanometer process. It only gets more expensive.
And if I remember correctly, I'm pretty sure the vast majority of things like PIC microcontrollers, I think they're still in the 200 nanometer range. I think thereabouts.
I'm not sure about PICs per se. They're probably not quite 200 nanometers. They're probably a little bit more, so maybe sort of 90 or so.
Oh, because energy efficiency and stuff, isn't it?
A lot of mixed signal or analog devices are done in very older generation technologies because they don't have very high performance digital requirements, and actually for a lot of the analog, it's better characterized in older technologies, and the cost per unit area of wafer is much lower. So why pay the premium to put it in a more advanced technology when you don't actually get any benefits from it?
From my experience,
so certainly something like radio frequency identification, RFID, most of those devices are still made in 130 nanometer or above.
And I'm just sort of thinking back to my university time when I was doing VLSI. And from what I remember, it's like obviously digital circuitry. The smaller you make it, the more energy efficient, the faster you can switch, and all that jazz. But with analog circuits, it made no difference because it's based on physical characteristics. Like, so if you're making a resistor on a semiconductor, it has to be a certain width and a certain length, a certain height, and all that kind of stuff. So you don't care about the 3, 5, 7 nanometer. You care about I need something that's like 10 microns by 10 microns, especially if you're making a capacitor or something. So and so that's what you're saying is that. When it comes to newer, it doesn't matter how far people like Samsung take their sizes on their chips. What matters essentially is what you can do with older generation technology and how it's still relevant. And that's what you're targeting as a company, because like you said, you're not interested in creating the world's fastest flexible processor at 3 nanometer, because no one needs it. And even if you could make it, no one would need it. It's a case of you're trying to target markets that are still using older generation, but it's more used. In fact, I would actually go as far as to say that when I think about modern technology, 3, 5, 7 nanometer, I can't really think where it's used besides high-end data servers, maybe graphics cards for the latest games and stuff, and things like AI systems. I can't think where you would want to use a 7 nanometer processor. Maybe a mobile chip, but beyond
exactly.
that,
I think the really intelligent brains of all of our devices definitely benefit from those. So,
of course,
even in something like a mobile phone, because we expect so much of our mobile devices now, there is value in continuing to progress the increased complexity and sophistication and reduction in power that you get from that progression of Moore's law. But as you say, there is a lot of stuff that doesn't require that. And we see our market for what we do really in two main categories. One is those more mainstream older generation technologies where even with our technology, even though we have lower performance than silicon, it's still good enough for the function that's needed in those applications, and we can bring this huge benefit of an improved form factor and lower cost to it as well. So that's sort of one category, is almost substituting for where you might otherwise use silicon, but actually we can do it in a more efficient way. And then secondly, there's a whole category of creating new applications that don't currently exist because they would never make sense with silicon. And so when we think about the sort of most exciting applications that people are using our technology for, it's putting it in things like packaging for fast-moving consumer goods in order to create recycling and reuse models. And that's something that just would never be economic with silicon, and actually fitting a rigid silicon chip into those form factors is also very, very challenging. There's ways you can get around it by using bare die silicon and thinning it and so forth, but they all, again, generally just add cost into the solution in order to make it fit into that kind of product category. So it's just not done. But actually with our technology, it opens up this whole range of opportunities that don't currently exist.
That's an interesting point, actually, because I was thinking in my head, because you said, like, looking for areas where we can integrate a technology that does better than silicon in the same area. So, for example, RFID tags and stuff. And I thought to myself, I've taken apart those before, and I've always seen those tiny little dies. And I was trying to think, what advantage would a pragmatic device have over something like that? But then you said that to make those chips smaller, it can be more expensive to do that, because, like you said, you have to thin the wafer.
That's right. So if you look at RFID as sort of perhaps the most common case where people have tried to use silicon to drive low cost and thin, flexible form factors in the end product, because you can make the antenna thin and flexible. So actually, if you can make the chip small enough, you can still get to a product that could be integrated into something like a label or a package. But as you said, the challenge with doing that is, in order to achieve that, you have to make the silicon die very, very small. That immediately creates challenges because your dicing of the wafer and the losses you have in dicing chips as they become progressively smaller, the amount of area you lose in the dicing lines between them, and the challenge of physically dicing them effectively enough becomes greater. You also have a challenge that the handling of those very small chips is quite difficult, and so you have to be able to pick them up, you have to be able to place them very accurately onto the antenna. That all has constraints in the models you can use for the assembly of those devices. So by contrast, with our technology, you can actually afford to make the chip physically much larger. It's still very thin, but in terms of its lateral dimensions, it can be much larger. So by contrast, a typical silicon die for RFID might be something in the region of 400 by 400 microns in XY dimensions. Whereas in our technology, you can actually make it cheaper while still making it physically much larger, something in the region of a few square millimeters. And that has benefits in terms of how you handle it, the accuracy with which you need to place it, the types of adhesives you can use to attach it, and even has some direct improvements in terms of what you attach it to. If we take something like near-field communications, NFC, the antennas for NFC are basically a loop antenna. And so the way you create that is you make a coil on one side of a substrate, and then you have to physically connect the outside of that coil to the inside of the coil in order to close the loop. Now, with our technology, we can make the chip big enough to actually span across the antenna and close that loop without having to do a separate layer in the antenna structure itself. So what we found is that where people are using our technology, there's not just the benefit of the chip itself being lower cost, but taking advantage of that thin, flexible, and typically slightly larger XY form factor means they can save costs elsewhere in the process and create a much more efficient overall solution.
So if we take a look at NFC stickers, RFID stickers that you typically see on product packaging, I think they're about maybe 3 by 3 centimeters or so, maybe 4 by 4 ish.
It depends very much on the application.
And so what I'm wondering is, are the things that you can produce at Pragmatic, could they be, or would it be not economical to have something that's 3 by 3 centimeters, so it's the entirety of the sticker is the IC, because then you could integrate the coil into one manufacturing process?
It's an interesting question, and we've sort of looked at that quite closely. Although we are much lower cost than silicon per unit area, we're still much more expensive than the normal processes you might use to make an antenna. So The general answer to that is in most cases no. There's certain physics that dictates that for a given application where you want a certain read range or a certain certain ability of sort of how you actually communicate with the chip, that tends to dictate your antenna size. And if your antenna is larger than, say, a square centimeter or so, it's going to be cheaper to make in a more optimized process to make that and then attach the chip. There's also reasons to do that just down to things like yield. The larger you make any chip in silicon or in our technology, the more that impacts yield. And so actually, it's part of the reasons why in the silicon world, people are driving towards chiplets and things like that is, actually by segmenting the problem, rather than trying to make monolithic, very large chips, often it's actually more cost effective to make a few small chips and join them together because you get advantages in how you yield the entire solution. So as a general rule, even with our technology, it still makes sense to have a separate antenna in an optimized process that is the right size for the physics of the read scenario you're trying to drive, and then you attach a chip to it. Having said that, there are some cases where the type of environment you're driving can have a sufficiently small antenna, or indeed moving away from an antenna entirely towards capacitive coupling rather than inductive coupling, where you can get rid of a separate antenna. And so we've certainly seen a couple of applications where we're doing custom chips for customers, which include everything you need, including the comms and the antenna structure within our flexible integrated circuit.
And so, to me, that suggests that if you look at the economics of your process, it's not so much that the construction of an individual chip is expensive, but the process per wafer size is almost like a fixed cost. So the more wafers so basically, the more chips you get on each wafer, the lower the cost per chip. So you can't make a wafer with like 5 chips on, and it's still a lot cheaper. So you can just, because I'm just sort of envisioning like pieces of plastic that have little sort of like semiconductor areas, and if you're only having to produce that area, that makes it cheaper. But it's not. It's the entire wafer is done in one go.
Yeah, the dynamics are broadly similar to any other semiconductor manufacturing process. That it essentially, for a given process and number of layers within the stack and so forth, it is a certain cost per wafer and hence a certain cost per unit area. And if you don't use some of that area efficiently, and sometimes there are good reasons not to do that because it does save when you look at the overall cost structure. But yeah, generally you still, all other things being equal, the smaller the amount of area you can use, the cheaper you can make it.
Interesting. I think it was yesterday or maybe 2 days ago, I wrote a report on Electropages about disposable electronics. And one thing that sort of caught my attention is that Pragmatic is looking in the direction of disposable electronics. Is that correct?
It's certainly one of the key areas. So if you take perhaps the simplest way to consider that is to look at examples for what happens with consumer goods packaging. So this is one of the key areas where people are using our Rfid technology is in plastic packaging for consumer goods, where you want to drive a better outcome for a circular economy. And there's essentially 2 ways you can do that. One way is you improve the recycling outcomes for the packaging. And there the RFID has the benefits in being able to identify the packaging, to be able to communicate to the consumer via technologies like NFC. So actually they can tap it with their smartphone, they can know then how to dispose of it to best effect. And within the recycling stream, that packaging can be very clearly identified. You have all the data around what the packaging is composed of and hence how it gets recycled most appropriately. So in that sense, yes, it's driven to sort of single-use disposable packaging, but still driving a better outcome for the packaging by adding that functionality into it. The other approach that we've seen increasingly common is people driving reusable packaging models. And so there, the benefit is if you have packaging that is perhaps slightly more robust than conventional consumer goods packaging, it can be reused multiple times, with a cleaning and washing cycle. And that has obviously a better outcome from an environmental perspective. But again, there, the ability to identify that packaging, to track what it's being used for, how many times it's being used. At some point it will degrade to the point where it does need to be taken out of circulation and properly recycled. The ability to add that unique identity into it via something like RFID is hugely beneficial. So yeah, we see both these applications of both single-use models where you can drive an environmental benefit by having that intelligence in the packaging, as well as reuse models that are, for certain product categories, even better outcomes.
So my question then about the use of recycling is, so the advantage of having essentially smart packaging is that it allows you to track. So one thing I've seen, I thought was quite interesting, was the idea of a product passport, where as it goes through different parts of its life, basically you can track where it's been, where it's going to go, all that kind of stuff, and how to recycle it. So let's say you have an old box and you're not sure how to recycle it. You can give it a quick tap with your phone and it says, oh, this product contains this is how you dispose of it. So it can help with that process. But my question mainly is more focused on the actual chip itself, because one concern I personally have with disposable electronics is, especially the traditional silicon technologies do contain a lot of toxic compounds. So when they're buried in landfills, they will leach chemicals over time. It might be very tiny for one small chip, but you add that into the billions and you might start to see buildup of certain heavy metals and stuff. So my question is, has Pragmatic looked at that as a long-term thing, and are there like chemicals or compounds that you're trying to remove from your products?
So yes, that's definitely been a key focus for us in terms of really three aspects to the entire product life cycle. Firstly is the manufacturing process itself, which is, if you're going to be making billions or ultimately trillions of these devices, then actually reducing the energy consumption, water consumption, any chemicals that are adverse to the environment, or just general carbon footprint, be able to reduce all of those things in the manufacturing process is absolutely critical. And so that's been something where, to be honest, slightly by accident, it's fair to say, we designed our process to optimize for a particular thin, flexible form factor and very low cost. It turns out that a lot of the decisions we made there have also given us a situation where our process is about 100 times more energy efficient than silicon manufacturing and about 1,000 times lower carbon footprint overall.
But the question is,
having found that, we're now improving it further, understanding that that's a key driver.
But for me, the question isn't really about CO2 in general. I mean, I'm going to be a bit of a cynic here, but I'm honestly not that bothered about CO2 as much as I'm bothered about things like ozone depletion, stuff like that, and forestry stuff. So what I'm saying, I'm not interested in the energy consumption side of it. I'm more interested in the actual compounds used to make
the materials.
So if they were buried, what would happen essentially?
Yes. So for a certain set of customers, actually the energy and carbon footprint of the manufacturing is important. So that's sort of one key element we look at, and it's a key focus. But you're right. Then when you look at the product use and how that ends up at the end of life or end of use of the product, again, there's two key aspects to that. One is the components of the chip itself, and the other is what it gets integrated into and how it can influence those materials as well. So within the chip itself, our flexible ICs have nothing that is basically a contaminant in the environment, and in fact, they can go through standard recycling processes, like a plastic recycling process, and effectively just be part of that process rather than be something that either is physically separated before it goes into that process or ends up being a bit of grit as a silicon die would be in those processes. So the recycling of the chip itself is actually very straightforward, and we've had a number of customers who've done analysis of all of the materials within it, in terms of everything to do with food safety, child safety. If a child swallows it, does this cause any problems? As well as things like recycling and what does that end up in? And there's no issues in that regard. Where there's even greater leverage, I'm saying, is what it gets integrated into. So again, if we take a simple example like RFID with silicon is almost always integrated onto a PET-based substrate with an aluminium antenna on it. And that is the most cost-effective option today, and it's the only one that's sort of really scaled in volume. over time, there are better solutions for that in terms of the processes that are used to make the antenna, the chemicals that are used in that, and also, what happens to the recycling of that antenna structure. And so what a lot of our customers are also working on is how do you evolve that to be able to use things like printed copper antennas, for example, on paper substrates. And it turns out that for a lot of the reasons I mentioned before, using a thin, flexible, larger area chip actually makes it far easier to use something like a printed antenna than if you're trying to do that with a very small bare die silicon. So that's the sort of three main areas we look at is, the environmental impact of the manufacturing of the chip itself, the end of life impact of the chip, which is a fairly clean in terms of the types of materials that are used, but also the leverage in terms of what the chip's being integrated into and how it can actually improve the overall recycling or environmental impact of what it's being integrated onto.
So it's like a multi-pronged attack on environmental concerns and stuff. So it's not just a case of, well, to be fair,
perhaps it's worth highlighting the reason why that third piece is actually quite important is, the size and the amount of material in the chip, whether it's us or a silicon chip, is actually very, very small. Now, you're right that over time, as this goes into billions and trillions of things, that is still important to look at. But actually, the even more important parameter is, in any case, this chip is going onto an antenna that is several square centimeters, on a larger substrate of some kind. So making sure that is appropriate in terms of its environmental impact is actually far more important than the chip itself. The chip itself becomes important once you've made sure that the larger thing it's being integrated into also doesn't have an environmental impact.
And from what I understood from what you said, it sounds like you're suggesting that the integrated circuits that you are producing at Pragmatic are certainly less of an environmental concern than the ones that you might find if you use standard silicon types of technology.
Definitely, yes.
I think you should go with that. Well, for me, it's a real concern because the idea of having billions and billions of disposable electronics it's one of those things I kind of feel a bit uncomfortable about, and that's because I know the kind of things that get put into silicon, standard traditional wafers, and it's not nice stuff. And so but if someone said to me, but Pragmatic Solutions, you use this, it's safe to the point where a child can swallow it, and you do have that sense of, well, that does sound like a better option. So that's a really interesting application, disposable electronics. But then this comes to the question about flexibility and why it's important. With Pragmatic, it seems like it's sort of two things. It's not just the fact that they're printed using plastics and stuff, so they're not based on silicon crystalline structures, but it's also the fact that they're flexible. So tell me a little bit about why flexible circuits are going to be something that's important for the future.
Sure. And I think it's probably worth adding that actually the thinness is often important as well. So the thinness and the flexibility both come into play. And firstly, it's worth saying that not all of these parameters are important for all applications. So it kind of varies a little bit by application. But the reasons thinness and flexibility are important, one of the main ones is that when people are putting stuff into a product that is not a box of electronics, usually that is because the primary purpose of that product is something other than the electronic functionality you're adding. Yeah. And again, Rfid is a very simple example of that, where the primary purpose of the packaging is to protect the food or whatever else it's enclosing. The Rfid is a supplemental function in order to improve the way that's managed through the logistics chain. But actually, what it can't do is impact the primary purpose of the packaging, which is to protect the thing it's enclosing. So making the form factor as invisible and non-invasive to that thing it's being integrated into is often quite important. And so, for example, if you look at doing this with a silicon chip, even though the silicon die can be very, very small and can be thin to a certain extent, you still have a bump from that silicon chip. Yeah. If you put that into a roll of labels or a roll of packaging, particularly if the chip is placed sort of at the same place in each package, when you roll that up, you end up with that bump starting to sort of accumulate. So it actually creates a lot of challenges in the operational model. You can get around all of these things, of course, but they all require additional cost or additional material in order to get around that. Similarly, when you look at it when it actually gets applied to a bottle. If you can think about a label being applied to a bottle, if you've got a small bump in there, that's actually visible. That's an issue from the marketing folks because they put an awful lot of effort into the look and feel of the product and the graphics and everything like that. And if you've got this bump that visually stands out, that's not great. It's also, again, an issue from an operational perspective because, if that's on the side of the bottle and they go down a bottling line where they kind of jiggle around and get bashed against each other, the silicon chip can very easily get knocked because it's got no protection of a normal package that you might have as a silicon chip in your PC or mobile phone. The silicon chip can get fractured very easily.
And the issue with adding that extra protection is that it's going to make it thicker.
Exactly. Yeah. So you end up with a thicker label, which really isn't what they want because you want to make the label look as seamless as a normal label. So that combination of thinness and flexibility in our chips means you can integrate it into these kinds of form factors without any material change to the look and feel or the operational model of how that material is handled as it goes through its life. So that's the kind of main benefit. Beyond that, I guess I'd say, and if I come back to this category of applications that people never thought about doing but now can do, there are a set of things where thinness and flexibility in the electronics is absolutely critical to be able to make something work. And so you think about examples like sensors that you might need in a wearable smart patch to do wound monitoring that you can't do with a very small bit of silicon because you actually need to sense things over a somewhat larger area. So you need physically something that is of a certain size. Another example might be large area sensors like fingerprint sensors, for example. At the moment those are all made rigid, but they have to be a certain size because they need to be big enough for your finger. There's no point making them smaller. So with those, if you can get the advantage, if you want to integrate that into something that fundamentally needs to be thin and flexible, there is no way you can do that with silicon. Whereas with our technology you can. So that's again, the two angles we see is for things where you might otherwise be using silicon, we can improve the look and feel and operational model to make it easier to integrate. And then you can create these new applications that fundamentally require thin, flexible circuits, and there's really no other way of doing that today.
And I'm just sort of thinking about the fact that you said it's kind of, what you're really saying is that you kind of want to get these circuits to be discrete and essentially not go undetected, and so that kind of makes those types of that makes those kind of integrated circuits embedded to the truest meaning of that word. So when we talk about embedded electronics, we say things like, "Oh, we put a microcontroller into something small, and then and it gives it some functionality." But what you're saying is, no, we're going to put electronics into that product, and you won't know it's got electronics, but it's in there, and it's a part of the packaging, and it's like because I've seen pictures of the Pragmatic wafers, and I mean, and the colors that they have, you could almost use it as a label. In its own right, you could wrap that around a container, and it would look good. But all of that is electronics. And so you can add functionality while having absolutely no sign that it's got something in there in the first place.
Yes. So one way to think about the way our electronics gets embedded to things is that it is a material. It's not an electronics product. It is a material that gets incorporated into the end product in the same way that any type of special plastic for protecting something from as an oxygen barrier or things like that might be. It's a functional material. In our case, the function it adds happens to be electronic, but it's still viewed as a material that gets integrated into the product rather than being a specific electronic device that's whacked on the side to do something.
So does that make Pragmatic one of the first companies being viewed not entirely from an electronics point of view, but actually, like you said, a materials company?
It's an interesting way of looking at it. We kind of try and straddle both sides of it, if you like. So on the one hand, we are a semiconductor manufacturing business, and so a lot of the ecosystem we interact with is exactly the same as if we were a silicon foundry, the global foundries and TSMCs of the world. The way we operate in some respects is very similar to them. We run a semiconductor manufacturing process. We provide a process design kit for people to be able to design anything they want on our technology, and we manufacture wafers for them. Where that starts to deviate from that is when you look at the types of applications and as we were just discussing, the sort of models for how people integrate that into their product. those are very often non-electronic devices that they're being integrated into.
Yeah.
So whereas the vast majority of silicon chips are made for an electronics customer who wants to put it in a box of electronics with lots of other types of electronics, our customers are often, people like large consumer goods brands or packaging companies or toy and game companies. And, most of what they do is not electronics, but this is an opportunity for them to add an electronic material into what they make. And so, in that sense, although fundamentally we're a semiconductor manufacturing business, the reason we have a sort of applications team and our own in-house design capability is because often we need to help our customers take that step and understand what they can do with the technology, because they're not used to doing electronics design and manufacturing.
And so what Pragmatic is targeting, it's not targeting traditional electronic applications, because that's what your silicon dies for. You're trying to target companies who don't use electronics, but they could. And so what you're offering is a solution that allows them to integrate electronics into their design that's truly embedded, that's not going to be noticed, but can add smart features into those products without having a little bump on a label like we discussed before about RFID tags, for example.
Yeah, I mean, that's exactly right for, I would say, one portion of our addressable market. And as I said before, we see it in sort of two distinct categories. There are those ones that you've just described extremely well, which are companies that don't currently use electronics who have an opportunity to now use it in a way that they never thought they could. But then we also actually see a number of applications where people are using our technology, in some cases to replace silicon, but actually as often as not to complement silicon. Again, silicon has a set of strengths that we don't have. It's had decades of Moore's law. It's able to do higher performance. It's able to do low power. If you look at what's in your average electronic device, and you open up, your mobile phone, it's going to have a couple of large ASICs, which are doing all the really complicated stuff, and they're really leveraging the potential of silicon. But then you typically have a large PCB with a dozen or more other components that are doing relatively simple things. What's often called glue logic. It's just the bit that makes everything else connect together well and does the analog interface to the antenna or things like that. And so we're seeing applications where people are basically saying, all of those other small components that never make sense to integrate into the ASIC because they're all slightly different for every different PCB you design with that same ASIC, actually with our technology, because not only is the cost of the chip very low, but actually the cost of designing it and speed of taping out new products is dramatically faster than silicon, then actually you have the opportunity to actually redesign the rest of the product that doesn't use the high-end silicon. So this perhaps builds off one thing we kind of haven't really mentioned yet, which is that one of the unique aspects of our process that we kind of never really anticipated how important it is the fact that our production cycle time is dramatically faster than silicon wafer manufacturing, because we eliminate those really complicated energy-intensive processes like in ion implantation. Our process start to finish to produce a wafer is around about 24 hours. So as compared to a typical silicon wafer production process, which even if you rush things through is typically 3 months or more, and
I've seen lead times going into I have seen some foundries quoting 12 months.
Yeah. Well, I think we probably need to be slightly cautious there. So at the moment, the reason for 12-month lead times is not because they're starting production now and it takes 12 months to get through the process. It's because they've already pre-sold all their capacity. And so
I see what you mean. Yeah.
It might be 6 to 9 months before you actually get
okay. Yeah. So TSMC,
I see. Challenge, even if you move away from the current supply-demand constraints in semiconductors, the most fundamental challenge is, even if your fab is empty and you've got nothing else happening in it, and you want to produce a wafer for somebody, it still takes you several months to do that because of the duration of all the processes you need to create a silicon chip from a raw silicon wafer. Whereas by contrast, for us, that is around about a day. So even when you build in production scheduling and all of those kind of things, we're typically going from circuit tape out to production wafers in less than 2 weeks. And that dramatically changes, when you combine that with the fact that the cost of a tape out is 100 to 1,000 times less than it would be for a silicon ASIC. That means you can now think about these things like taking glue logic and doing a custom chip just for this one PCB. And that still makes sense because you can get that in the same timescale that you would normally have for buying the PCB itself. And you can do it at a cost that isn't that different from designing the PCB. And then you have a solution that no longer needs this large PCB with loads of small components on it just to make the whole solution work. You can compress all of that down into something that is more compact, thin, flexible, much lower cost. when you think about devices like wearables, where the entire focus is how do you make this in a form factor that's as compact and wearable as possible, actually that potentially is quite game changing to some of those applications.
Now, it's interesting that you mentioned wearables, because I report on researchers creating new wearables every day, and I have to admit, I get a bit frustrated sometimes when I see these researchers say we've made a wearable TEG and it generates power for our circuits, and you realise it's this great big massive ring on their finger with a huge heatsink, and it's never going to be bloody practical. And one thing I've always moaned about when it comes to wearable electronics is that, as far as I'm concerned, they don't exist yet. We've got smart watches and we've got smart glasses, but I don't consider them wearable in the same way as maybe a shirt. So if you can integrate if you can put an integrated circuit into a shirt with sensors going around it, and I don't know it's in there, and it's organic and flows with my skin and my body, that is when I'll consider something wearable. And I suppose what you're saying is that pragmatic integrated circuits, that's one potential area going into the future.
Exactly, and I agree. I mean, we've heard people sort of describe, even a smart watch is sort of your classic wearable, but basically it's a box of electronics strapped onto your wrist.
Yeah.
And it's as good as we can make it at the moment, given the constraints of what we have with electronics. But when you say actually you can fundamentally change that form factor, people are working on flexible displays, flexible batteries. Yeah. And we kind of solved the in some senses the missing piece in that, which is how do you make the active electronics flexible as well. And so you're right. Things like wearable technology integrating clothing is one opportunity there. I think probably the biggest opportunity we see there that our customers are driving is around healthcare wearables, where so we've got a number of projects where people are basically looking at different types of functionality where the electronics is already quite well understood in terms of how you monitor an ECG signal, for example, or how you monitor a wound. But at the moment, it has to be done via very bulky electronics that is only viable in a hospital. But actually, if you can take that electronic functionality and translate into something that is the same form factor as a Band-Aid plaster, but it still monitors the wound that's underneath that because it's got the electronics integrated in to do that, that actually becomes very exciting, particularly if you can make that for something that costs less than $1 and you could buy it, in your local chemist. That actually is quite game-changing in terms of, the type of wearable functionality that can be enabled.
The area which I think I would personally say is probably the most important when it comes to wearable medical actually is the fact that when you give if you can give patients wearable sensors that a doctor can remotely monitor, you can send the vast majority of them home, and they don't have to sit in a hospital where they might pick up secondary infections, because I do find hospitals a bit of a joke, because you go in with one condition, you come out with another. And it's a serious issue for people with heart conditions, where if you have like open heart surgery, and if you see the wards which they live in, they don't live there. Sorry, the wards which they're kept in, especially as a kid, I always remember big doors. This was before COVID, and I remember big doors saying things like "wash your hands before you come into this area." It's because those patients were so vulnerable to secondary contamination, and so if you can put these wearables onto people who've just had operations, you can send them home, keep them away from other people, and then from there they can recover in their own space, which is better for them mentally. But then they're monitored wirelessly by a doctor using sensors that, like you said, cost a few dollars.
You're exactly right, and I think there's even taking it one stage beyond monitored wirelessly. In some cases, you can allow the patient to take control of their own, their own data, without needing the doctor's intervention for that. The other big application I see, you're exactly right. This is all about how do you personalize healthcare and make it more able to be deployed in environments that make sense. The other huge benefits of that, one is what happened, how do you stop people going into hospital in the first place? Can you monitor conditions that today are hard to pick up and avoid that hospital, visit in the first place? So, another project we're working on, for example, is an ECG patch for detecting atrial fibrillation. This is something that's a very common condition for people over 60, but it only gets picked up today when you have an AF episode, and then you go to the doctor and they have to do all sorts of complex analysis to try and decide whether it's something that needs treatment of some kind. But actually, if you could, again, go to your local chemist and buy a wearable patch that you stick on for 2 weeks and it'll detect if you've got that problem, it can pick up those sort of symptoms much earlier and allow them to be dealt with in a very different way. The other huge advantage we see in these kinds of technologies of being able to make them more ubiquitous, low cost, easy to access, is making them more available outside of developed countries. We obviously have despite the a lot of the challenges the NHS has, we have a great healthcare system in this country, and everybody has access to it and can go and access it whenever they need to. You look at places in sub-Saharan Africa and so forth. There isn't that same infrastructure. There isn't the ability to deploy it. There isn't the budget to be able to do it. There isn't. But actually, if you can change that to a model where it all happens via wearable devices, and actually be able to leverage the smartphone is quite interesting there, because interestingly, smartphones are quite prominent in those kinds of environments. It's often their main way of communicating with the rest of the world, or things like that. So actually, you can still leverage the smartphone as a communication platform to analyze the data and be able to tell people what's doing. But you need the sensors and the ability to make those very low cost and very easy to access for everybody.
Well, I have to disagree on one point where you said that the NHS was an excellent health service. I mean, my experience has not been that good. So no, but I understand what you're saying. But by comparison to everywhere in the world, it's still one of the best systems compared to everyone else.
As a free service where they have to prioritize.
Oh, it's not free. You pay for it. You pay for it through taxes. That's what national insurance is for. But there is something interesting you actually mentioned there. And this has never occurred to me, but it has been in the back of my mind. You said, when you go to these sort of areas, maybe, I don't know, the poor areas of maybe India, the African desert, that kind of thing, everyone's got a smartphone. And you don't have to be that many generations behind to have something that's pretty darn powerful. And I remember as a kid where, they had all these these sort of charities to try and bring IT and stuff to Africa and to try and get them into the technological age. But then you find that all the efforts of trying to get big desktop PCs over there and big old style monitors is completely pointless. Because smartphones in their own right are cheap anyway. And you can drop a couple of thousand of them. It doesn't cost very much. And suddenly you've got access to almost everything.
And one of the main reasons for that is power.
Yeah.
So, if you could give somebody.
Oh, that's a good point as well. Yeah.
And they have no electricity at home. What are they going to do with it?
But all they need is a small solar charger. And considering the fact that most of those places it's sunny for at least half the day, you can charge everything during the day and have access to something during the night. Because I know that one big contributing factor to development, educational development, is having light at night. Because the moment you have light, you can read, and when you can read and you can do things, you can keep yourself occupied in other ways. But if you've got a smartphone that's producing its own light through a screen, it could be pitch out. And you can scroll, read, do whatever you want to do. So, but relating the smartphone to healthcare, and I kind of feel like that the next, not the generation below us, but the generation below them, I would say maybe my grandchildren, I've got a feeling that they're going to be the first generation where everybody is monitored from birth, and so if you have if people are paired to a smartphone and a bunch of sensors, you can monitor every aspect of your medical history from the moment of birth. And if you power that with AI and then using things like pragmatic, flexible sensors that can stick onto the body, you would pick up things before they even become an issue. And it's always quite interesting how, and I'm not sure what your experience is on this, but I do feel like that doctors are quite negative towards AI sensing technologies that can diagnose people before they have a chance to look at these things. And I find there's a lot of resistance in that area.
I think so. The whole topic of AI, I think, is interesting, both in general and as it relates to our technology. So perhaps as a general statement, the way we see what we're doing is very closely related to the evolution of AI and machine learning, because AI fundamentally requires access to large amounts of data in order to develop in the best way. And we've got very good at generating digital data around things. So, you think about why is Amazon so successful? It's because every click you make when you're on the Amazon website is recorded, and so they build up a profile of who you are, and they know what you're going to want to buy, and they can make you buy more things. But when you try and translate that into the real world, getting information about physical items, that's far more difficult. And so one sort of generic way we think about a lot of what we do is adding electronics into, to making everyday items smart. so that they can be part of the, not just the Internet of Things, but the kind of the Internet of everything. And if they can communicate to that in some way, even if it's just identifying them uniquely, that already brings value with things like RFID, but you start adding sensors into the mix and you get an even richer set of data around what's happening to physical things in the real world. So that's sort of the generic starting point. In terms of when you come back to the sort of healthcare, I think you're right. One of the challenges that I think we have in the healthcare, particularly in the West, is around privacy of data. And so the reason why the medical industry, I think, has been somewhat reluctant to embrace AI is a combination of privacy issues which constrain having access to the broadest possible data sets to really make that work effectively. And secondly, it's around liability issues that at the end of the day, the way our system is set up is, if a doctor is responsible for you, they are responsible for what happens. And if you've got an AI system that's making a decision based on an algorithm that's been learnt and you can't prove why it's making the decisions it does, you kind of always need human oversight of that, the way things are currently structured. Now, I think what we were just talking about before is the more you shift the control and gathering of data towards the individual patient rather than the system, you get around both of those issues to a certain degree. If somebody's collecting all their own data, then actually you can have systems that make decisions based on that without it having to go outside the environment. So this is, I was on a panel for this actually the other day where, there's sort of an interesting debate between how much of AI and machine learning is going to happen centralized in data centers and how much needs to get pushed out to the edge. And, the answer is obviously going to be a mix. There's some things where you're going to have a more efficient solution if it's all collated in a data center, but there are other scenarios where, for privacy reasons or whatever else, or latency reasons, actually being able to push that out into the end device is important. And so that's why we see the combination of increasingly powerful smartphones that have the ability to run, machine learning algorithms natively on the mobile processor, combined with the types of sensors and things we can enable, is incredibly powerful. And actually, over time, we even see there's potential to push that out into our devices themselves. So we had a really interesting publication in Nature Electronics 2 years ago, which was around an electronic nose sensor. In this case, it was for odor, but you could evolve the same kind of underlying functionality to things like some healthcare applications or things like air cleanliness or food freshness or things like that. But the key thing there was we actually integrated the machine learning algorithm within our flexible IC as well. So although we can't compete with what silicon could do if you need a billion transistor machine learning system for a smart car, actually when you bring it down to a specific problem of actually we've got this range of sensors that are detecting this concentration of volatile organic chemicals, and you can have an algorithm that's designed just to, based on that, detect whether there is a problem in the environment or not. That can be done very effectively in our kind of technology, and then you push the entire thing right into the sensor, including the machine learning algorithm.
And so really data is king in all of this. It's all about data at the end of the day. Yep. So integrating electronics into non-electronic applications, it's more about the data it's gathering as opposed to the product itself.
Yeah, and I'd perhaps tweak it slightly. It's about data and it's about compute capability.
Yeah.
So you need the data as the input, and then you need the compute capability.
Yeah.
And what we see is there's a range of models for that, but at a minimum where we fit in is we're helping provide more data into that system. And over time, as we improve our technology and as the algorithms become more efficient, you can actually drive more and more of that compute functionality further and further into those individual items themselves, so that they can make those decisions without having to even necessarily be connected back into the rest of the ecosystem.
And so I kind of want to shift the conversation towards the actual technical side of the flexible chips, because one thing that, if I understand correctly, the logic type that your devices use is NMOS logic. Is that correct?
That's correct.
And so that I take it that sees some energy consumption issues because of the fact that NMOS uses a resistor and it uses a pull-up resistor with an NMOS pull-down. And so whenever you've got something that activates, it's pulling current down to ground.
Broadly, yes. So I mean, NMOS obviously means we only have N-type semiconductor devices. Now, with that, there are a number of different logic architectures you can implement with different pros and cons, including some things that are generally termed pseudo-CMOS, where you can get some of the benefits of CMOS even with only N-type devices. So there are ways around some of those constraints, but just as we saw in silicon back in the late 70s, early 80s, if you can evolve from NMOS to a CMOS architecture, that has huge benefits in terms of not just power consumption, but also things like noise margin and yield and so forth. So, we are actively developing CMOS, and we have it, working in R&D, but not yet transferred into our production process. The reason for that is not a fundamental one. There are, the types of materials we're using, these thin film materials, there are P-type materials as well. But the reason that takes a little bit longer is the way you optimize that into a proper scalable manufacturing process is non-trivial. And so if you think of the reason why we have actually managed to get to the point we have, where we can make very high yielding devices in these kinds of circuits, and pretty much everybody else who's tried to do this has never got past doing it on an academic worktop, is because it's very easy to make a one transistor in a lab on a Friday afternoon when everything goes well. That's very different to having a proper semiconductor production process that makes a transistor with exactly the same characteristics every time you make it, and can make thousands or millions of those within one circuit, all in spec at the same time, to be able to yield a complete integrated circuit.
That's quite interesting. You mentioned actually about the scientists getting it on a Friday morning. Yeah, the number of times I have to report on advances in research, like I said with the wearable TEG, it's phenomenal. The speculation that a lot of media will go to. So like I said, you'll get someone. Here's a good one. So there were some researchers who created a solar panel, and they said that, we've created one that generates energy at night as well. And the first thing I thought to myself was that no, that's not going to be the case. Read into it, and they said, so basically the solar panels can harvest the latent energy of the Earth as heat, so they can charge devices and power homes and stuff. I thought, yeah, but how much energy are you getting out of this thing? And it turned out you'd need an acre's worth of solar panels to charge a phone. And they jumped from this idea of generating 75 milliwatts from this entire array to it's now going to power homes in Africa. And I just thought to myself, like, there's a lot wrong with that.
Well, to be fair, there's a lot of innovation relies on a certain amount of unbridled optimism. Most of the steps forward we have don't happen unless someone is sufficiently naive to go and do something that everybody thinks is impossible, and they make it work in spite of the consequences. So I can't actually. I don't actually have a problem with that optimism in research, but you're right. Actually, I think it's interesting from a press reporting perspective of there needs to be a bit of a sort of sanity check sometimes on these things. And we looked at this, for example, as we were developing our technology platform. The company name is very, very intentional. Pragmatic Semiconductors. We are very pragmatic about everything we've done over the last decade or more is about developing this platform to make flexible integrated circuits that can be very low cost. And we have no technology religion in how we do that. So we don't care whether it's printing or non-printing, whether it's organic or metal oxide or silicon or anything else. We just happen to end up with something that works because we've taken the right set of trade-offs of how do you drive the right cost point, how do you drive the right manufacturing process and yield. And as an example, sort of along the lines of what you just described, I remember very early on looking at some of the other technologies for using organic semiconductors that could be printed using an inkjet. Exciting idea. You can do additive printing. Conceptually, it sounds really good, and there were exactly the kinds of press reports you talked about. This means you could print everything directly onto the packaging, and because it's additive, it will be lower cost and everything like that. But actually, when you work through the exact material consumptions and things like that on it, it turns out that even if you wanted to do something as simple as an NFC chip, given the feature sizes they were working at and the types of materials and so forth, you would end up with that entire chip about the size of an A4 sheet of paper.
So it's not exactly practical.
Very integrating thing. And the amount of material you use doing that, even though it's additive and you're not putting material anywhere you don't need it, because it takes up so much area, and you're printing very thick lines of the semiconductor material, it ends up using thousands of times more material than the kind of thing we've ended up doing, where we're depositing a 10 nanometer thick layer of a material, and yes, we use a subtractive process to pattern it, but the total amount of material in it is so minuscule that it really doesn't matter.
And so when you say about, because thinking about the practicality side of this, and then you're saying how you're working on CMOS technology in R&D, is the challenge that is it that you can make P types and N types individually, and you can make them? So, for example, could you make an entire wafer that's P type, but you can't mix the two together? Is that the issue?
It's a combination of a lot of things. So so one of the fundamental ones is it a material that can be properly controlled to get the right consistency and yield in a high volume manufacturing process?
Yeah.
And that, for a variety of reasons, is harder with P-type than M-type. There's elements around having consistency and mobility between the P and N-type in order to get the proper benefits of CMOS. So you can accommodate some difference in mobility between the materials, but if it's too great a difference, it just doesn't work effectively. Right. And thirdly, it is, as you say, it's about some of the process interactions when you try and integrate those together. So, broadly speaking, it is about not the fundamental concept. I mean, CMOS, thin film electronics, has been demonstrated well over a decade ago. We've demonstrated it multiple times over the years. Our partners have demonstrated it. Doing it on a bench in an R&D lab is pretty easy. Translating that into a high yielding manufacturable process with the right consistency is where it gets difficult. And so that's what we've really been focused on for the last several years is the right material set that can have the right level of control, that gets integrated into the right process, that does this with a high yielding process that still preserves the kind of cost structure we've got at the moment.
And so if we talk about cost, because I think cost is one of the biggest factors, or that and speed, because I think, because you were saying it's like a 24-hour from initial, from the, you can essentially, from the first layers to the final product, you've got about a 24-hour window, which is honestly hard to comprehend. Because I mean, like you said, even the fastest semiconductor manufacturers out there will give you maybe a 3-month if you're lucky, and that was before the semiconductor shortage. So my question in that is, well, to start off the first question, have you been approached by other companies during this shortage about what it is that you're capable of doing? Yes.
I can't say a lot more than that. So perhaps the only thing I can really expand on for that without sort of breaching customer confidentiality is some of what we've been discussing around these applications to replace silicon are things that we hadn't really thought of a couple of years ago. And it's been the combination of increasing maturity in our platform to be able to do more complex functionality beyond things like Rfid that sort of brings us into a level that is essentially comparable to what you might do in a mature node silicon process in terms of functionality. So there's been an improvement in capability on our side that's enabled that. But the other key driver has been the constraints that our customers are seeing that they can't get hold of the silicon that they're used to doing. So they're kind of looking at other options. And actually, one thing that that is quite interesting in those cases is, well, actually, if with our technology they can replicate the kind of functionality they need, that has immediate benefits just in availability and lead times beyond all of the other advantages of cost and form factor. We do see there are a set of applications that are being driven by that dynamic. We're slightly cautious about those because if it's only about lead time and 2 years from now that's going to resolve, we don't want to be spending our time and effort doing products where we don't actually have a fundamental advantage. But where we see that often translates to the desire for strategic control of supply chains in the future. This is obviously a huge issue across everywhere. We just had President Biden sign the CHIPS Act in the US. There's the EU got the CHIPS Act.
That's right.
China's been investing in trying to build domestic semiconductor manufacturing capability for years now. Japan's just announced a new program for it as well. So every country is kind of very much aware now that semiconductor supply is actually a strategically important capability, and if they're reliant on other geographies for it, that's a bit of an issue. We see that actually extending even further to the individual company level. So where we're dealing with large companies who have high volume use cases for our kinds of product or even for conventional silicon, they see that as a direct issue in managing their supply chain if they've got long lead times or unpredictable lead times or just the inability to guarantee the capacity they need for their own product. Then actually there's a really interesting option for them with our kind of technology or being able to have a dedicated fab. Again, one of the other things we haven't sort of mentioned yet is another flow-on benefit for the type of process we've developed is that not only is it much lower cost, not only is it faster cycle time, but actually the physical footprint and capex needed for a fab is orders of magnitude lower than it is for silicon.
Including price?
A factor of 100 to 1,000 times lower.
In price as well?
Yeah.
Blimey.
Yeah.
But interestingly,
that means, and so to give an idea of that, your typical semiconductor fab would be hundreds, if not millions of, hundreds of thousands, if not millions of square meters of clean room space.
Oh, easily, yeah.
TSMC's Fab 18, I think it's something like 200,000 square meters. Our fab is a few hundred square meters in total footprint.
You can put that in my back garden.
You can put that in any manufacturing environment and be doing just-in-time manufacturing of ICs.
That's phenomenal
for the customer. And every day you can change the product mix because a day later they'll have product out the line.
You see,
they've got 100% guaranteed capacity because it's on site where they need it.
Well, this is where I think that companies like Pragmatic, you might end up creating a new industry in its own right, which is localized manufacturing. So instead of waiting for TSMC, sorry, instead of waiting for TSMC to give you a bunch of chips in 6 months' time after you place a custom order, you have one of these sort of things that fits in a shipping crate, and then you drop it in your factory, and it just starts spitting things out after 24 hours. But there is one question. Not a question, I suppose more of a statement and a question, which is that if Pragmatic doesn't have foundries in the US, you know that CHIPS Act works against you.
All I can say is stay tuned.
Stay tuned. Because one thing that's really bugged me about this CHIPS Act is that it says like that it's to promote US foundries, US semiconductor companies. It doesn't help US fabless companies because they still rely on people like TSMC. So what's going to happen is that people like Intel, TI, and I think maybe Micron, they all have their own foundries, so they get all the benefits. But people like AMD will severely suffer from it, and Nvidia as well.
Actually, there are provisions within it for foreign companies to build manufacturing in the US, and that's covered by the CHIPS Act. So TSMC could build a factory in the States.
Of course they could do, but this is but here's the issue. How long is it going to take to make that foundry? So it's going to take them years to do that. So by the time that they finally got there, all that CHIPS Act money is probably going to be gone. Intel's going to be having a laugh because they're chucking things out with their foundries because they're the people who are going to benefit from that act will be the ones with foundries right now. The ones who want to build them, they're going to take years to get into the game.
Actually, a lot of there's a number of different aspects within the CHIPS Act. Some of it will benefit existing foundries, but a lot of it is oriented towards building new capacities, either from domestic suppliers or foreign suppliers, but physically manufacturing in the US. And so that is directly relevant to Pragmatic as well.
If you fabricate.
So our plan over the next decade is to have at least 100 fabs globally, producing over 1 trillion items every year. And some of those will be in the States. And
absolutely.
They fit very well into the what the CHIPS Act is trying to do. In fact, I had the pleasure of meeting with Senator Warner, who's one of the key architects behind the CHIPS Act a couple of months ago, and he kind of put it very well, where he said, the potential of Pragmatic's technology is not just to have 1 or 2 new fabs in the States; it's to put a fab in every state within the US.
Yeah. And that makes complete sense.
Consider having a semiconductor manufacturing industry now have the potential to do that for a relatively small capex investment, and they get the benefit of the skilled jobs creation, but also all the ecosystem benefits around that. Because it's not just about having the manufacturing; it's about next to that, then you can encourage all the assembly and integration and the design and all those kinds of things benefit by having the manufacturing.
But then companies like AMD and the fabulous companies then have to rely on the fact that other foundries will open their doors up in the mainland. So until they do, they're either reliant on someone, because I think Intel's thinking about becoming a foundry for other people, because they've talked about it.
They've announced that they've set up a separate.
That's right.
Division, part of the company that is specifically focused on foundry. So that's an explicit strategy.
So then AMD suddenly becomes reliant on someone like Intel to make their own products, which is kind of weird, and which gives Intel an unfair advantage in my. Well, AMD and Nvidia came out and they themselves are not happy about the CHIPS Act because of the fact that it does penalise fabless companies who use technology from or use foundries outside the US. It does bother me with some of these acts because it doesn't. I understand why they're doing it, because even I hate the idea of all of the world's most important semiconductors are made within like maybe a 1,000 mile range in the southeast of Asia, where China and people like that are sort of eyeing this tiny little island off their coast, thinking, this is going to be good for the taking at some point, and then suddenly the world's supply of semiconductors just goes down the toilet. So I do understand why they're doing the CHIPS Act. I like where it's coming from, but I think it doesn't appreciate the fact that semiconductors really do take a long time to establish, and then you've got things like environmental red tape as well. So that's going to stop new foundries from coming up in certain places. So yeah, I don't know, maybe TSMC says like, oh, we want to set up in Austin, and then some local committee says, oh, we're worried about the environment, and then suddenly it can't get bloody built, and then you have to keep then sending them to Taiwan.
I mean, I think the reality is there's no simple answers to these things, but I think that's where what we've been trying to do is sort of say, well, how do you rethink some of these fundamental things? So, part of the challenges we have with that is that the lead time for putting a new fab capacity is so long and so expensive that constrains things. Now, to a certain extent, when you're looking at sort of 3 nanometer, 5 nanometer, there isn't an obvious way around that. But actually, when you look at some of the other applications that don't require that technology, there are interesting ways you can rethink the problem and you can make it simpler. And so I think what you said before is kind of how we view it, is that we have an opportunity here to actually create, in a sense, whether you define it as a new industry or a new way for the industry to expand capacity, which is much more modular. I think the equipment vendors actually, I think, really like that as well, because they're used to these very, very large boom and bust cycles of, at the moment, everybody's building fabs, and, part of the reason the lead times for fabs are so long is because everybody's placing orders with equipment companies at the same time. And, 2 years ago, nobody was placing any orders. And, so they can never manage their capacity and their business very effectively because it goes through these huge boom and bust cycles. Whereas if you can evolve that to something where actually fab capacity is added on a much more modular basis, then you avoid that big swing, because you can be continually adding incremental capacity. And, if you get a little bit ahead of demand, then you slow it down slightly. If you get a little bit behind, you speed it up slightly. But it's minor changes to trajectory rather than sort of everybody building fabs at the same time and then 3 or 4 years later nobody building fabs. That's kind of what the industry's been used to.
And then one thing that sort of keeps going through my mind is when you said about it being very modular, especially the fact that you only need a few hundred square feet to produce your devices. It kind of makes me wonder then that what's really to stop you from replacing a traditional semiconductor device? I'm not talking about the latest tech. I'm talking about like your analog op amps, that kind of stuff. What's to stop you having a facility like that where you create your own little op amps and then you package them inside a standard IC package and you just take them out like a standard silicon die, and then immediately by doing that you've eliminated the need for long lead times from current foundries. Now I appreciate you said that in the next 2 years it might all catch up and then suddenly you can get those other devices cheaper, but if you are a company who wants to protect their own supply chain, what's to stop you from doing that?
Nothing. This is exactly the discussion we're having with a number of customers, and you can. I mean, it's funny you say the sort of idea of packaging it just like a silicon component. I mean, obviously the biggest advantage for our technology and applications where the ability to have no package at all is actually what people are taking advantage of, the thin flexible form factor. But we have done some things where we basically put it on a little micro PCB with some legs and it looks like a DIP component and can go into a breadboard just the same as a DIP component would.
And to me, that sounds like it could open up a lot of opportunities in the world of ASICs as well. So if you're if you're a company who wants to design their own custom chip because they need very specific logic, if you do that with a traditional silicon ASIC, that's going to cost a lot of money. I think I remember figures being around £10,000 when I was at university. I don't know if that's still the case, but I know that ASICs are very, very... Oh, keep in mind, that was a university, and I think it might have been... They were a part of other companies who put their chips on the same wafer sort of thing. So
you can do what's called a multi-party wafer, where you basically get a small area of the design area. That generally doesn't work very well for volume production. So that's sort of fine for prototyping and first iterations. Yeah. But actually, if you then need a regular supply of it, it's quite difficult to manage that. Because you're dependent on everybody else wanting the same volume at the same time for that wafer to be produced and things like that. So you're right, there's huge challenges in that innovation supply chain, and perhaps the kind of most extreme way of thinking about that is if you think about the what happens in universities in training the next generation of designers. one of the big issues at the moment is you can teach everybody the theory of how to design a chip, but it's very hard to actually give them practical experience because it's very expensive. And even if your university has the budget to be able to do that and have a multi-party wafer that every student has a small design on, you don't get that back until 6 months later.
Exactly.
And by that point, everybody's on a different module and have forgotten what they designed in the first place. So, we started exploring this with a couple of universities where they're basically integrating into their undergrad electronic engineering design courses, where within a semester or within a term,
that's phenomenal.
Everybody in the cohort can design their own chip, and 2 weeks after tape out, they'll have it back. They can test it, see what worked, see what didn't. What mistakes did they make? What did they learn from it?
VLSI was my favorite subject in electronics, and it always has been. And I swear, I would have given up a left arm to get a chip made. And the idea of having something made like that from Pragmatic is phenomenal, absolutely phenomenal. Because there's nothing quite like testing something in real world in a real world scenario. I mean, you can do all the simulations in I think it was, what was it called? It was like Spice or something. I can't remember what. Tanner Tools, I think it was called. Tanner Tools. Yeah, that's the one we used. And you can do all the simulations you want in it, and it works. But when you get it built in real life and you see it operating, it's just nothing quite like it. Yeah. Now, I suppose we've got our last question, and I think, on reflection from everything we've talked about, I think the best question to ask would be, what are the current restrictions that you're currently facing, and where do you want Pragmatic to go in the next sort of 10 years?
So in one sense, the biggest restriction we face is there are so many exciting things people want to do with our technology, and we can't do it all at once.
Yeah.
So for us, it's about focus, and in some cases we're having to not do things that we'd really quite like to, because they're not just going to drive the biggest top line revenue growth in the near term and things like that. So a lot of my focus at the moment is working on expansion plans for the business. We raised $90 million in Q4 last year. We'll shortly be announcing some additional funding. That is all basically driving towards how do we continue to expand both the capacity of our production. So we're in the process of building our second fab at the moment, which will increase our production capacity substantially, as well as being the sort of reference model for these fab as a service opportunities I was describing before, being able to put them anywhere around the world on site in customer premises. So it's basically driving forward that model and making it a reality is really what we're trying to happen there. And in parallel to actually expanding capacity, it's also about expanding our organizational capability to be able to do that. We need the right team and the right people to be able to grow that. So we've essentially doubled the size of the company from about 100 to about 200 staff within the last 12 months. And we'll need to continue to grow that in order to have the organizational capability to support that. So that's internally what we're focused on. In terms of the external challenges that constrain that, while our offering in many respects is really well timed in the current global supply crisis, the one challenge we do have is availability of production tools, because we're buying from the same semiconductor equipment vendors as TSMC and everybody else. So lead times to deploy new capacity are not as quick as we would like them, and so that's one thing sort of strategically we're focused on. Over the long term, how do we change that dynamic and allow us to deploy new capacity much more rapidly? The other one for us is the ability, in terms of scaling the team, is access to talent. I mean, the UK obviously historically had a good semiconductor manufacturing industry, but that's largely disappeared over the last couple of decades. Where we're based in the Northeast is partially there because that's where historically there's a good base of semiconductor manufacturing expertise, but it tends to be in people later in their careers who used to work in the industry 20 years ago and are really excited about coming back to it and being involved with something where we're actually expanding and building capacity. But we do in the UK have a huge gap sort of in the younger generation of people that have that semiconductor expertise coming through. So we're putting a lot of effort into working with government and with the other semiconductor companies that are in the UK to sort of grow that talent pipeline over time. And obviously in the short term, it's a lot of recruiting people from overseas, and we've been fortunate with the coverage and the profile we've got with our recent fundraising and some of our customer activities that we've been able to attract people coming from the conventional semiconductor industry have the right skill sets we need to be able to grow this in the UK.
I suppose it doesn't help that a lot of companies have sort of shifted towards the fabless model. So it means that you do lose the foundries, and so the only thing your company can. So you look at ARM, for example. They're a fabless industry, and while that does mean they've got lots of talented people who know how to design silicon chips, they haven't got anyone who knows how to make them, and so you're reliant on a third party essentially who's not in the country.
Yeah, I mean it and this sort of comes back to. Part of what you need is an entire ecosystem. It's almost in some sense that's where the similarities and challenges in the States is. In the US, there is a similar dynamic where they're a leader in design and EDA tools and so forth, but have fallen behind in semiconductor manufacturing. And part of the motivation for increasing that is not just about solving critical supply chains, but it's about if you don't actually have all those pieces of the ecosystem, you lose something fundamental in understanding how all the bits fit together. And so we, in the UK, we work very closely with companies like ARM. ARM's actually a strategic investor in the business. And so, we actually see companies like them in the ecosystem are absolutely critical, working with their design expertise and their IP and so forth. But you're right, I think what we can help bring back to the UK is also having a strong domestic capability in the manufacturing side of things, and that actually enhances the entire ecosystem.
Thank you ever so much for being here with us on this podcast today for Electropages. And do you have any closing remarks before we end this show?
No, just thank you very much, Robin, for your time. I think it's been a really interesting discussion, and hopefully it's opened up the eyes of some of your audience a little bit to the possibilities of what can be done outside of silicon chips when you take a new approach to semiconductor manufacturing. Oh,
absolutely. And I hope that you come back at some point to talk more about the applications for flexible devices, because like I said, we touched on things like artificial intelligence and medical diagnosis. So I think that has a lot of, that could be a conversation in its own right.
We'd be happy to.
Fantastic. Thank you ever so much.